Let's look at energy flows really from a global perspective and think about what it takes to run this economy that, I'm using the word to really indicate the sum of all our human activities, products, services, and whatnot, everything we do that generates wealth, part of the economy. This is just a simple thermodynamic flow diagram, right? I mean, we see the Earth as a system in space with energy input from the sun. You can't read the color on this screen very well. This says infrared thermal radiation going out. The basic concept here in this illustration is, well, clearly there are finite resources. And there's also, as people sometimes forget, a finite capacity of the planet to absorb waste, which by the second law of thermodynamics, we understand there has to be waste, whether in the form of heat or material waste as well, that can be recycled and put back in, make things more efficient, but not indefinitely. So this view is really that of the planet as having a finite capacity to support economic activity. An emphasis in the discipline of economics, of course, historically has been on efficiency. And without perhaps denying the finiteness of the planet, saying, well, we really can get a lot more value and worth out of doing things better and smarter and more efficiently. So the question is not so much, is the planet finite, but really, are we anywhere near having to think very seriously about running up against the physical limitations of what is the volume of an economy that we can sustain, what is the volume of activity we can sustain. Clearly, it cannot be infinite. And I argue that the first place we run into that constraint really is in terms of the carbon cycle. So looking at the natural carbon cycle, the circulation of carbon in living and non-living things in the ecosphere, roughly 50 billion tons of carbon per year being sequestered by photosynthesis, being exhaled by animals or bacteria. Human activity emitting carbon, ooh, and the red is just not coming out of this projector. There is a red color missing on the projector. What this says is CO2 emissions approximately equals 7 billion tons per year. So the 7 gigatons of carbon emissions per year, anthropogenic, are a pretty significant fraction of this natural carbon cycle. In other words, the scale of human activity is meaningfully similar to the scale of natural processes without humans. That should give us pause. Now, there is also a small arrow going back from the atmosphere, carbon being removed from the atmosphere, and you can't read it. It says approximately 3 billion tons of carbon per year. We'll come back to that. But we all know this. Yeah, still doesn't help. It's a little better, perhaps. We all understand that the emission of carbon in the form of carbon dioxide into the atmosphere is causing this infrared absorbing layer that's increasing surface temperatures.
Let me ask you a question. Is the amount of light okay for your camera?
Yeah. Very well.
Yeah, because if you want more light, let us know. All right.
Okay. Great. Thank you.
That's what good to see. More light. Yeah, the red. Oh, I'm disappointed about the red. I had some nice colors in these slides. This is just in case you hadn't been paying attention to everything that's been in the news over the last 10 years or so. There actually is serious warming going on. And more interesting, I think, to people in this room might be the point that climate scientists have actually become quite good at explaining past temperature trends and thus can feel reasonably confident about predicting future temperature trends based on a number of variables of which carbon dioxide concentration is only one. Right? And I'm not going to go through this list. This is not really a lecture on climate change, but just to make the case that if we take our best models and we feed the data into them, our models actually do a very good job of predicting past temperatures. So the climate scientists know what they're doing. They have some good data and some good analysis. This is just to show you a few pictures that will not be entirely new to you of evidence that climate change has happened already over the past decades. Glaciers shrinking. This is just over the past 2 years. The Arctic summer ice shrinking from 05 to 07. Surface melting on Greenland. And this is sort of what it looks like on site. A lot of ice going into water. Come on. Oh, this is not wanting to work, so I'll use the arrow key. So ice is melting, disintegrating. This slide would make a lot more sense with the red. What it's showing is essentially the distribution of warming that is already occurring. The point is, it's not really so much the average warming that we should be worried about in terms of the effects of climate change. You know, a degree or 2 Celsius doesn't sound like a whole lot on average. What the concern is really about is there are patterns where the temperatures are increasing a lot more in certain parts of the planet than in others. In fact, some areas may be cooling, but patterns, global climate patterns, are shifting in ways that may lead to qualitative changes, the climate being a complex system, that are not easily predicted. So that has other consequences, increases of fires. There was a lot of red in that slide, for instance, and really, you know, questions about extreme climate events, the frequency of flooding, hurricanes, but also droughts on the other hand, productivity of agriculture, and higher order effects, the spreads of tropical disease vectors, for instance, right, in shifting climate. Agricultural productivity really being a big factor. So, in a nutshell, I would say it's not about global warming, it's about global weirding, which has been said, or global climate disruption, really. So, let me come back to the question of the carbon that's being removed from the atmosphere, because the carbon is actually, CO2 is actually not accumulating in the atmosphere as quickly as we would expect based on the rate at which we're emitting it, the 7 billion tons. And for a while there was really a puzzle among the scientists saying, well, where does the difference go? And does anyone in here know if 3 billion tons a year, roughly, of carbon dioxide are leaving the atmosphere, where could they possibly be going? Indeed. Again, oh, the fish were pink. Well, there it is. Now, why is CO2 in the oceans a problem? How does CO2 get into the ocean? It dissolves in water, just like in your sparkling water, not quite the same concentration, and makes carbonic acid. So it will then, and that arrow goes both ways, you can squeeze it into solution, right? And there's an equilibrium that tells you how much carbonic acid you're going to have in solution depending on the partial pressure of CO2 above the water. And so as the CO2 concentration in the atmosphere is increasing, it gets driven into the oceans, dissolved in the form of carbonic acid. And so while we weren't paying attention, the oceans have become more acidic. Is that something we should be worried about? Well, the pH of a solution depends what other things are soluble in it. And a more acidic water is going to have higher solubility of calcium carbonate. So the calcium carbonate is very important in the marine food chain because there's many marine organisms, the pretty seashell, but also the corals, that depend on the chemical equilibrium that allows them to use the carbonate, the calcium carbonate, to build their bodies. And this slide, I've actually stolen some slides from John Holdren here, who's now President Obama's science advisor. This is reassuring to me that John Holdren, who is a very knowledgeable energy expert and knowledgeable on climate matters, is advising our president. This shows acidity of, well actually the graph is a saturation of a certain form of calcium carbonate showing historical trends, and basically to say that the chemistry will not be favorable for these marine organisms to make their carbonate shells. The implications for marine food chains and ultimately fisheries, I don't know who's done estimates on this yet, but are possibly devastating. I mean, it's not just about the coral reefs are very pretty if you go snorkeling. You know, it's really about the productivity of that ecological system. This diagram is intended to give you a little bit more of a visual on the whole stocks and flows of carbon through the ecosphere. And really we have to distinguish between the stocks, the accumulations, and the flows, which are the rates of movement. So we have actually a lot of carbon in the rock here that's uninteresting because it's underground and it stays put. Next to that, the largest inventory is actually dissolved carbon in the oceans. And this is measuring again in units of trillions of kilograms or billions of tons of carbon. So we have, I keep having to edit the slide because the atmospheric concentration keeps increasing every time I teach the class. But you see the carbon cycle, the natural carbon cycle, roughly 50 billion tons per year. We're cutting back on that due to deforestation. So we're actually interfering with the natural carbon cycle also by reducing the rate of sequestration. But the really important thing that we're doing as humans is we're taking carbon that has been chemically bound underground in solid or liquid or gaseous form as a fossil fuel, and by drilling and extracting it and then combusting it, we're adding this previously underground carbon into circulation. Right? So we're taking these 7 billion tons of carbon per year and putting them into circulation. Now some of them are being absorbed here into the ocean, but you can see from the picture that's a kind of a temporary storage, because once in the ocean, they can come back out. Right? Being dissolved in ocean water isn't a permanent disappearance of carbon. So there's actually quite a reason to be concerned about those 3 billion tons of carbon going from the atmosphere into the ocean. Partly because of the chemistry of the ocean water, partly also because they're not permanently in there. In fact, what do you know about the solubility of gases in water? How does the solubility of a gas like carbon dioxide vary with temperature? What happens to your fizzy soda water when you keep it in the refrigerator as compared to when you leave it on the warm kitchen counter? When you have it warm, it goes flat much sooner, right? Because the solubility of gases actually declines with temperature. It's backwards from when you're trying to dissolve a solid like sugar or salt in water. So now here's one example of a rather scary feedback effect, because as the planet warms, the oceans will warm, meaning that the solubility of the CO2 is going to decrease. That means some of it may bubble back out. So it's not a permanent disappearance of that carbon. But really, what's at issue is this carbon that's now inserted, that we're bringing into circulation, if it were left underground, would be out of circulation, would not be at risk of interfering with the climate system there. So that's something that we've got to stop doing. Historically, it doesn't look so good, because here's the rate of increase of burning fossil fuels, using fossil fuels. I mean, this even doesn't go back to the beginning of the Industrial Revolution, and fossil fuels here include coal, oil, and natural gas. And this really for a while looked like an exponential kind of increase. And some people are assuming that, well, it may, the energy consumption rate, energy demand may yet continue to increase exponentially. Those are typically the business as usual scenarios. This one by the Intergovernmental Panel on Climate Change, just sort of drawn there for reference to see, well, wow, that's a lot of energy demand. And the question becomes, if we really need that much energy, then what color marker are we going to use to fill in the area under this curve? It can't be this brown marker for fossil fuels. I want to briefly point out a common conceptual problem, which I believe is the reason why many well-intentioned people who believe climate change is real and something needs to be done don't feel much urgency about the problem. And the misconception has to do with the confusion of stocks and flows. You see here the historic increase of carbon emissions and carbon concentration, CO2 concentration in the atmosphere. Many people look at these graphs and say, well, look, this curve, and then of course the temperature change curve, they all have the same shape. So they're correlated, right? Now, people, without thinking analytically about it, draw the conclusion that if we want this CO2 concentration curve to flatten out or decline, what do we have to do? Well, we should perhaps have our carbon emissions curve flatten out or decline. There's an assumption that the two are going to be paralleling each other in shape, which of course, as you understand as engineers, you understand a stock flow diagram, it doesn't work that way. Because a better analogy here would be to say the carbon dioxide concentration in the atmosphere is an accumulation. It's like the water level in the bathtub. That's how much carbon there is in the atmosphere. The carbon we're emitting by burning fossil fuels is the rate at which we're adding the carbon to the atmosphere. So that's the inflow. The outflow is the carbon leaving the atmosphere, currently going into the oceans. And if I ask you, well, if we want the water level in the tub to stop rising and stay constant, what is the constraint that imposes? Well, for the water level to stay constant, the inflow must equal the outflow. Right? So this says if we turn down the faucet and reduce the inflow, that doesn't mean immediately the water level is going to go down. It means it will rise more slowly, and it will stop rising at the time when the inflow equals the outflow. If we want the water level in the tub to go down, well, then we have to get the inflow less than the outflow. This is not rocket science. But in fact, you might be surprised to hear that a study of MIT engineering students as subjects found that 70% of them could not relate this concept to a question about climate change, because people aren't in the habit of using stock flow type of reasoning in application to environmental problems. So the message is think bathtub when you're talking climate. This is really what a lot of other people think about in stock flow diagrams, that is the inflow comes from somewhere and outflow, what outflow? Doesn't exist, right? But so the bathtub model really tells us that in order to stop the increase of carbon dioxide in the atmosphere, we'll have to dramatically reduce the carbon emissions. It makes sense because we can't keep taking carbon out of the ground and putting it into circulation. To stabilize the concentration at 450 parts per million, which already commits us to a 2-degree average Celsius increase. So that's already a different climate than what we've ever had. This is not a no-problem scenario, but this is a lesser change than these other scenarios. To achieve that, we have to immediately stop growing and, in fact, reducing our carbon emissions very dramatically and get down to about 80% less than the 1990 emission rates by 2050, I think, is about where I remember the numbers being. This is another graphic depiction of it. So there are different kinds of scenarios of what CO2 concentration we end up with in the atmosphere. And to stay within this first scenario, which is the most survivable scenario, certainly the one that we can expect would support the greatest human population on the planet, to stay within this number one scenario, we can see that the emissions have to really decline very soon. So the shape, the time series diagram of the rate of emissions versus the amount of accumulation of carbon in the atmosphere are two very different looking curves. Right? That's what many people don't understand. So this is a big job that needs to be done. How do we get there? This is from a well-publicized study from Princeton University introducing this notion of climate stabilization wedges that is looking at different technologies or approaches to reduce chunks of about 1 billion tons of carbon per year, saying that, well, if policies support enough of these different wedges, we can add them together and stabilize. Now, you see what they're stabilizing in this picture are really the emissions. It's the rate of emissions. It's not yet stabilizing the CO2 concentration. Now, to get to even this, to the emissions rate to stay at about 7 billion tons per year, we have to do 7 of these wedges, which I'm about to tell you what they are, except because we haven't done anything since this was published, we now have to do 8. And the time sensitivity of this can't be overstated, because the longer we wait to take action, the bigger the mitigation effort that we have to do. I mean, this is like a project that gets bigger and bigger and bigger the longer we procrastinate it. This was a red arrow, I want to point out. So this red arrow shows that the emissions actually have to be reduced to equal the rate of carbon with removal from the atmosphere to stabilize CO2 concentration. But since we also understand the ocean can't keep getting more acidic and absorbing more and more CO2, really in the end, our net transfer of carbon from an underground repository into the atmospheric ecological circulation has to be 0, ultimately. 0 is a word that you haven't yet heard very much in the policy discussion about this. I'm hoping that I will hear our president say this, because, I mean, it's really going out on a limb in terms of the political dynamics of this problem, but from a scientific stock flow perspective, that's where we have to get, eventually. Now, in California, the governor has already signed the directive to get to 80% reduction by 2050. That's a good start. It's not yet saying the word 0, which is too politically charged, but the trend is certainly, the trajectory has perhaps the right slope. Let me get to these wedges, and really the main part of my talk today, which is to look at some of the options that we have for really making huge, meaningful reductions in carbon emissions. And I'm going to be focusing on decarbonization of power. That is, what can we substitute primarily for coal, or what can we do to coal to reduce these emissions on a very large scale? Essentially, I would argue that we have to do 2 things. First of all, we have to use energy efficiently. So I mean, as you saw, there are other sectors that are meaningfully involved with this, but now focusing on the energy sector, the first thing is we have to use energy efficiently. That's a no-brainer. I mean, in fact, those are negative net costs. Investing in energy efficiency, as any educated economist will tell you, has a really high rate of return. And there are, even with low-hanging fruit having been picked, energy efficiency improvements are paying for themselves very quickly. Our university knows this, which is why our university has built very energy efficient buildings like this one. Salazar Hall is a great example. So I could spend a lot of time, and I do in my other classes, talk about energy efficiency. You know, in my class you have to buy cookies for everyone. But in addition to energy efficiency, we need to look at, okay, the energy supply, what is it going to be? I will outline essentially 3 strategies. One is to keep burning fossil fuels but catch the carbon and keep it from going into circulation. The second strategy is nuclear energy to substitute for fossil fuels, and the third is a portfolio of renewables. So I want to tell you a little bit about what the constraints and the interesting problems are having to do with each one of these 3 strategies. Carbon capture and storage. Actually, people aren't really even quite settled yet on what the acronym CCS means. For some, it means carbon capture and sequestration. Sequestration meaning that you chemically use that CO2 and turn it into something else that might be stored more easily. Let me just list for you where I see the main problems. The first is that many people haven't thought about the actual volume of mass flow we're talking about here. A second problem is that if you're in the business of capturing carbon and sticking it somewhere to keep it out of circulation, there's no inherent incentive that rewards you if you do it well. There's nobody underground who will pay you for delivering them carbon, right? You don't get a reward. You don't get any kind of benefit from having added the carbon to a place underground, with one exception that I'll get to. But in general, in order to get companies to do this and to do it well, you have to write laws and then watch over them to make sure they do it, right? There's no intrinsic reward for them. So there's verification involved. There's a question as to, well, is the carbon going to come back out after you stick it somewhere? If it's still in the form of a gas, it sort of has a way of escaping and bubbling. spend a lot of money building an infrastructure for carbon capture and storage or sequestration, what that really means is we're committing ourselves to continue to extract and burn fossil fuels. So there may be a strategic concern about doing that. CCS is not something that we might just do for the short term because it's going to cost money to build the infrastructure. This is a little chemistry background to speak to that first concern, which is the sheer mass flow, right? What are fossil fuels? Well, coal is mostly carbon, a little bit of hydrogen. Oil or petroleum is a mixture of different compounds that are basically all chains or rings of carbon surrounded by hydrogen atoms in different lengths and shapes and forms and whatnot. And then natural gas is individual carbon atoms completely surrounded by hydrogen. So these are all hydrocarbons. Now when you burn a hydrocarbon, what you're doing, oh, and this was blue. How can this not show? It was a beautiful aqua blue color that was the hydrogen and the water. You really had to have seen the slide with the aqua blue, I'm telling you. So what this chemical, this is an imbalanced chemical reaction line here, this reaction indicates the subscripts X and Y could be different things depending on which fossil fuel we're burning, right? So for methane, CH4, it would be C1H4, but you could have different ratios of carbon to hydrogen in the different fossil fuels. What we see is we're going to get different ratios of CO2 and water as the two combustion products depending on which fossil fuel we burn. This is why natural gas is often referred to as a cleaner burning or a more favorable fuel compared to coal. Coal having the highest ratio of C in there. But the point of this slide was not really to tell you that, but to tell you something else. The point was to say that carbon dioxide is not a little fringe pollutant on the side. Carbon dioxide is the product that you're making in order to get the energy from this exothermic reaction. You know, it's not a small amount of CO2 that you could perhaps filter out from the rest of what goes up the flue. In fact, in bright red here was one rail car of coal in to the power plant results in roughly 2 rail cars of carbon dioxide product out. Right? So you have to visualize the mass flow at the facility that's doing the fossil fuel burning to say, okay, if you're going to capture or sequester that carbon dioxide, boy, are you going to have a lot of tons to deal with, right? It's not just a couple of boxes full of stuff. So what are we looking at? The technology really for pumping stuff underground is not rocket science. I mean, there's improvements made, but fundamentally we understand how we would do such a thing. How we might take CO2 as a gas and with high enough pressure in a deep well, stuff it underground somewhere. Depending on the geologic formation, we may be more or less certain that it will stay there for geologic times. But some examples are listed here: depleted oil and gas reservoirs. We know there's space under there, we could pump it down. Now number 2, use of CO2 in enhanced oil and gas recovery is actually an example where you do get a reward from being good at putting the carbon back underground because you're creating pressure and pushing fossil fuels out, helping you recover those resources. Now, if that's the incentive that we want to give is another question, because in a sense it really reinforces the societal commitment to say, yeah, we want to burn more fossil fuels, right? So it's a commitment to that strategy. There are coal beds, deep saline formations, offshore or onshore, and some other options. It's not trivial. There's technology involved. I think what's, and I don't want to go into the details of this, except to say, well, there's pipelines involved, there's mass transport of large numbers of tons of material, and there's technology involved, which we have to remember is to be invested in on top of the prime energy, right? So this is not instead of the power plant, this is in addition to everything else that the fossil fuels and the power plants cost. The map doesn't show up so well without the red, but that's looking at where in the United States we have potential candidate regions for putting CO2 underground. There's rather a lot. This is looking at where some of the largest point sources are. And you can see that power production is the majority, but not 100% of all the important point sources of CO2 emissions that, were we to get serious about not emitting CO2, we would have to capture. Now, note, point sources are on this map. We're not talking about vehicles or moving sources. That's a much more complicated problem, right? So the CCS really applies to the point sources. What you're really visualizing here is an extensive infrastructure of pipes and capture and pumping devices that would stuff it back underground. It's a larger endeavor than many people imagine. Now, here's my main concern. I spoke about the verification. A study of flue gas desulfurization, which is basically scrubber smokestacks from coal-burning power plants in China, found that the sulfur oxide emissions reductions that actually were measured were about a third of what they should have been, based on how much of these, how much of this equipment had been installed. So based on the number of power plants that had installed scrubber smokestacks, you would have expected these sulfur oxide emissions to go down by 3 or 4 million tons, but in fact, atmospheric measurements found that they were only decreased by about 1 million tons. How could this be? Well, in interviews that were done, it was found that the power plant operators said, well, the government paid us to install this equipment, the scrubber smokestacks. They didn't pay us to operate it. And the plant operates more efficiently without them. So you see that there was a negative incentive. And a lot of money was spent on manufacturing and installing equipment that ended up not being used. So now this is not an engineering problem. This is really a social problem, perhaps legal, economic problem. But in fact, if you look at this list of issues, I don't see the carbon capture and storage as really being so much an engineering challenge as being a very large investment and an economic legal problem of making sure it happens. Then, of course, there's a scientific problem of how sure are we that the carbon we put underground would be, in fact, permanently out of circulation. So those are the key issues I see with it. Let me go on to the other three, the other two strategies, and that looked better with red too, and see where the main issues lie here. Nuclear power has been much talked about as essentially a necessary evil, with the debate being about whether it's more necessary or more evil. I submit that it's in fact neither necessary nor evil. I think it's better seen as an expensive way to boil water that may or may not be too expensive. Here's John Holdren's way of summarizing the key question about nuclear energy, whether it's perhaps too vulnerable to human frailty, or human frailty may include either stupidity or malice, which means that basically you can't have Homer Simpson working your nuclear power plant. Nuclear energy, and I'm not going to talk about plant safety because that's not what's foremost on my mind when I think about issues with nuclear investment. In my mind, what's really serious is the fact that you have a very large and complex infrastructure investment that's necessary to make any portion of it work. You can't do a nuclear energy endeavor piecemeal, and I don't think you can do it readily in a private competitive market. I think it's something that requires large centralized planning and investment. No country in the world has executed a nuclear program without serious funding and direction by their government. There is a vulnerability to plans being behind schedule and over budget, which depending on how you look at it may be fair or unfair, but it's a fact of life that if you're building nuclear facilities, that you're likely to have protesters at your property borders, and you may get hung up in court somewhere. And so if you think about that as an investment risk, and you further think about the fact that for the entire production, the entire nuclear fuel cycle to work, every single component of it has to work. That is, the failure of any one component can cause the other components to be dysfunctional and not operational and not bringing in revenue. That makes it a pretty serious investment risk. Historically, there's been the issue of whether we can trust the nuclear industry. And then, of course, there's the business that you have nuclear materials that could also be used for making nuclear weapons. Seeing that the cat is out of the bag, and if you look at nuclear weapons on Wikipedia, you basically get a detailed enough diagram and annotations and instructions that with the people in this room, we could quite readily produce, if not a plutonium, then a uranium fission weapon, if we had the material. I mean, it's really something that a reasonably well-funded and educated group of people could do. That wasn't always the case, but the knowledge of how to make the bomb is out there. The real barrier is getting a hold of the materials, and so there's a question about, well, do you want people all over the world to have the technology to be able to make the fissile materials that would then also enable them to make a bomb? The trust and PR problem of the nuclear industry, I think, can be encapsulated in the fact that when people see this picture, they say, well, is that photoshopped? You know, we've always heard very positive and clean things from industries that have operated nuclear facilities, and sometimes that is so, and other times it wasn't so. It's understandable how they wouldn't want to fuel the, you know, tree-hugging environmentalists who are then protesting and waving banners and whatnot, but there's a real problematic dynamic here in that it's not historically been a transparent undertaking. Our department, U.S. Department of Energy, has changed somewhat in terms of being more transparent about its own, cleaning up its own facilities, but there's still a significant degree of public distrust and discomfort, which I would argue is simply a fact of life that as an investor, one has to take into account. This diagram of the fuel cycle, including the stuff on top, which we're already doing, and the stuff on the bottom, which we're not yet doing, is really intended to illustrate the complexity of this whole infrastructure investment, and to say that it's not just about the power plants, it's about building all the components that have to work seamlessly together to make this work. Here, just, well, this is a sense of the once-through fuel cycle that we're using in the United States, because as a matter of policy, we did not want to have on the civilian side this reprocessing technology, which then separates plutonium out of the fuel that could be used again for commercial reactors, having a very appealing sort of closed fuel cycle, sustainable feel to it, although it also produces waste. But this step in the cycle is, of course, what's used in the military sector for making weapons plutonium. So we've had a policy decision to keep these separate. If we were to expand nuclear energy to a very large degree, we would expect that this reprocessing and recycling of fuel, which allows you to greatly increase your efficiency of uranium use, we would have to expect that that would be reinstituted or advocated for. Certainly we'd have a serious discussion about it. So it's about a lot more than energy and the environment. It's about the politics and the weapons materials as well. Also often neglected is the fact that uranium mining is not a trivial undertaking. Like any mining, whether it's coal mining or any other metal, it's a dirty affair. Environmental Protection Agency had to spend roughly $1 billion just cleaning up this one site. And I just love this quote from the report: surface cleanup is nearly complete but has taken longer and cost more than anticipated. I would argue that's not an anomaly. That is something that happens with complex technical systems that require every single component to work, right? So there is reason for me to be suspicious of cost estimates for nuclear energy, because they have a way of being more expensive than you think they are. The uranium enrichment to make the fuel is a big industrial undertaking. That one in France. These are the famous gas centrifuges, which Iran also has, right? And there's a question of, are they making reactor fuel, are they making weapons? Spent fuel has to be stored, kept underwater, taken to the reprocessing plant. So these are big, expensive facilities that often don't get the photo ops, right? We often just look at the reactors. There's a reprocessing facility. Oh, and then you have to transport it. These are solid containers. I'm not worried about radiological hazard. I'm just seeing big expense and, you know, legal hassles. I mean, there is I don't want to minimize radiological hazards, but I think more has been made of it than, you know, technical experts might agree. But the thing is, you do have to move the material around. That means, again, you're subject to these political and legal problems, and you can't just, like Homer Simpson, toss it out of the car. So, essentially, a complex undertaking, and again, interestingly, the challenges here, the problems, are not so much engineering problems. There are social, economic, political issues. This is not a list of problems that lend themselves to being solved by engineers, really. Let's move on to the renewables. Here the main concerns are the availability of energy in space and time, and making it pay for itself, making it economically optimized, which is going to require being very, very smart. Now, what the problem with renewables is not, is a lack of resource, because the solar energy inflow here, incident solar radiation, 170,000 terawatts, that's 4 orders of magnitude more than global energy use total of all sectors, all sources. So there certainly is enough renewable energy there. The question is, can we use it economically and effectively, and can we get it in the right place at the right time? Here's just some pictures of the portfolio from biomass to hydroelectric power, photovoltaics, wind, solar thermal power, geothermal power. We actually have quite a remarkable repertoire of technologies that are off the shelf, that are commercialized, that are ready to go. Of course, they sort of seem to come in smaller chunks, and you can't just put them anywhere you want. Just some pictures here of large wind turbines. People are familiar with photovoltaics on rooftops. You see them around our neighborhood a lot. What we see less of, what's really a no-brainer and inexcusable for us not to be doing more of, is solar water heating. Domestic hot water is really pretty low-quality heat energy application, and it makes no sense to be burning a high-quality chemical fuel to make hot water if you could simply run it through a black tube on your roof. If you focus the sunlight with a parabolic mirror onto a working fluid, you can get it to very high temperatures to actually boil water and run a traditional steam power plant. This is a plant in operation in Southern California. It's not small. It also has the advantage that you can store the working fluid in a thermal storage facility, so you can produce electricity past the hours where the sun shines. So this is actually some help. Notice the acreage here. We've built hundreds of megawatts of these solar thermal power plants. It's more efficient from a land use perspective than photovoltaics. It's also less capital intensive. It's a lower cost per unit of power installed. So I see a great potential for considerably expanding the solar thermal resource. In fact, this little picture is just to show that the land area available is not the prohibitive factor. This yellow circle is actually indicating the size of the exclusion zone, the security exclusion zone around Yucca Mountain, which now may not actually be used. But just to give you a sense of the land area that's dedicated for the back end of the nuclear fuel cycle, if it were plastered with solar collectors, a little calculation, back of the envelope calculation, shows you that for an area of 1 billion square meters with 1,000 watts per square meter incident sunshine, converting it at 10% efficiency, you could generate 100 peak gigawatts of solar power, which is comparable to the peak power output of all the nuclear power plants in the country, right? Now, they don't operate 24/7, so at a capacity factor of 20%, this would produce about 5% of electric energy in the United States. Now, I'm saying this for the purpose of making the argument that land area is not the interesting constraint. Obviously, you wouldn't really want to put all the solar power into this little yellow circle in Nevada. But what you really want to do is you want to look strategically at a map of the United States, and you want to look at the electric transmission infrastructure. and say, well, where do we put what? Right? And you might conceivably start to fill in, well, there's the hydro here, the geothermal, the solar thermal. You need direct sunlight to be able to focus it, so you want to put it where it's dry, not where it's humid. You have the PV for where it's humid, because they can use diffuse radiation. Wind power, where you have wind. Biomass, where you have biomass. And you start to see a very different kind of problem. You start to see a puzzle to see, well, how can you fit these together and make them work? The interesting constraints now become the transmission infrastructure. In fact, this has been talked about because you have a vast wind resource here in the plains, but not enough transmission infrastructure to transport that electricity to where it is needed. So there is then a trade-off, an interesting investment decision between investing in transmission versus generation. There's also the question of cooling water. The picture I showed you before with all the solar thermal in Nevada, hypothetically, doesn't make any sense because you can't run a steam power plant where you don't have access to cooling water. Can't put it in the desert. So that was wishful thinking on my part. But nevertheless, there are places that, I mean, there is water. You have to think strategically about where to locate them, where to site these plants. And then the next variable is the time of day. And of course the weather conditions, right? When are you able to produce power? And how do you coordinate in time the different resources? Now my favorite slide here is this one that I absconded with when I was a consultant at Pacific Gas and Electric Research and Development Department 20 years ago. I was a graduate student. That's my favorite number on the slide, is the year 1989. Back in 1989, PG&E engineers studied how they might put together a 100% renewable electric supply system. And the analytic tool they used was this load duration curve, which looks at the electric demand in all the hours of the year, but not organized in temporal order, but organized by the amount of load. So taking some summer afternoon hour to be the top demand hour, and then ranking all the 8,760 hours of the year in order of decreasing power demand, you get this load duration curve. And you can see how the area under the curve has units of energy. So again, the question becomes, what color marker do we use to fill in different areas under this curve? And when you've filled them all in, you have met the energy demand. Of course, what you have to think about is, well, what resource is available during which hours? So here was an exciting modeling problem, and they found that, well, nearly a half could be, of the capacity could be supplied by solar, or the energy, 26.7% wind. You need some baseline generation that's actually operating 24/7 from hydro and biomass resources, and then you need some storage. How much storage? Well, this kind of analysis shows you. So you have pumped hydroelectric storage assumed here, and so this analysis showed how you would use your storage capacity to pump water uphill using electricity that was produced when perhaps the wind was blowing but the electric demand wasn't there. And then you let the water run downhill producing electricity during the hours when you need the electricity but the wind isn't blowing, the sun isn't shining. So it becomes a coordination issue. Again, what I think is interesting about this problem is that it was attacked 20 years ago. I would say that these coordination problems are actually the most real engineering problems of all the issues that I've talked about today. So in fact, I would argue these are also the most solvable, because they are issues that really would submit to a smart analysis, would submit to smart technical investment, and have really broad public support, and certainly have environmental arguments in favor. I would caution against trying to do what might come naturally to many of us, which is to say, well, we have these three strategies, let's see which one's the least expensive and do it. Because I would say that, well, they're all three expensive. No argument about that. Very difficult to accurately estimate costs, because things can happen. But they're very different types of supply systems that we could be investing in. So it's, you know, like if you're going to decide what sports your kids are going to do, like is it going to be soccer or volleyball or rock climbing? You're not going to decide that on the basis of, well, how much does it cost for the club fees and the equipment and whatnot. You decide that on the basis of, well, what sport do they want to do? So I would argue that this decision of which strategy ought we to pursue is really a question of what do we want to do? Which strategy makes the most sense to us, knowing that it's going to cost money, no matter which. I think an open question is to what extent these strategies can be mutually complementary. That is, should we be thinking of these three big strategies as supporting and enhancing each other, being part of a big portfolio, or does there come a point in time when an investment to do any one of these right is going to be so large that it will effectively preclude our society committing to the other two? And I suspect that may happen. I don't know the answer to that for sure. But I'm going to invite questions at this point, and maybe we should have the lights back on. We don't have, I'm sorry, we don't have a lot of time for questions. But yes?
You mentioned in the earlier net emissions. How do you calculate net emissions? You wanted those to eventually go to zero.
How do we calculate net emissions based, I mean, it's mostly done based on sales of fossil fuels, assuming that what fossil fuels got purchased will end up combusted, and we can do the math and figure out how many pounds of carbon are in that. So those models are based on, you know, inventories of oil, coal, gas production and sales. How do you get them to zero is basically not burn fossil fuels. So, you know, that's, you might say, well, that's a tall order. We're talking about really completely turning our way of life, our economy, upside down. And I really don't want to argue whether that's realistic or difficult or easy to do, but to say that from an ecological perspective, in the long run it's necessary. We could argue about how soon it is necessary to get there without lethal ecological impacts. But in the long run, from a simple stock flow argument, we could say we cannot continue to transfer carbon from underground into the atmosphere. I mean, if we take all those 9,600 billion tons of carbon that are underground in the form of coal, oil, and natural gas, and put all of those into circulation, that is, if we produce all the existing reserves of fossil fuels, I believe it would be catastrophic, and that's a consensus really among climate scientists. I don't think we'd survive it. So it doesn't become an issue of whether, but you know, how can we get motivated and educated and do it in the way that really is the most supportive of human well-being and the economy. Yes?
How much do you think the energy, shall we say, generating companies are putting their effort into this? Because all of these strategies that we talked about really require a big investment upfront. And I'm in fact glad that the present administration, in fact, is trying to put some money into this and so on to start doing it. But at the same time, these generating companies and power generating companies and so on also should somehow, you know, give in and then maybe help.
I think the real issue for private investment has been trying to assess the investment climate for a long enough time frame to make prudent financial planning decisions. And I think that's true not only for renewables, and I know many people in the renewable energy sector who say, you know, we would invest more, but we don't know if the tax credits are going to be there or expire after a year. We can't make a corporate planning decision if we don't know what kind of subsidies are going to be available. I think the same is true in the nuclear industry, that people are saying, you know, we could be, well, we're doing some R&D, but we could be spending more money, but I'm not going to build a nuclear power plant unless I have some assurances that, for instance, the licensing process is going to be streamlined. And so wanting to know what the investment climate is going to be in the long run. I think we're really dealing with a conflict of timescales. Because the type of argument that I'm making and what we're asking industry to do is to be thinking on a longer time scale than the political process has a rhythm of, happening on the shorter several-year time scales. So the challenge in the decision making that I see is to really shift our time horizon for decision making to a longer horizon encompassing decades into the future, rather than what's going to be profitable next year or the year after that, because that's not going to give the incentives. Yes?
Yeah, I have a lot of interest in this smart grid.
Yes.
And I know that it's a huge problem in getting the energy that can be delivered from green energy sources to where it needs to be. I know there's some committees right now that are working on doing a definition of this. Can you just give us an idea of how long it might take to install a smart grid and what it might cost?
That's funny because, well, no, it's not funny. It's a good, very good question. I have no idea how to answer, how much it might cost. Transmission and distribution infrastructure investment, even dumb T&D, is expensive.
Mm-hmm.
And many people are shocked when they find out that, gee, the existing infrastructure is very old-fashioned and, sort of ancient. It's a miracle that the lights stay on, if you really think about it. Much of the kind of communication and controls technology that we're really talking about really coordinating different nodes within the complex system to function well with each other, and hopefully in a way that's robust and not vulnerable to someone planting a computer virus somewhere and the whole thing goes down, right? I see that very significant developments could be attained within a decade. And certainly on the time scale that it's necessary to keep up with the increasing penetration of renewables in the grid. The state of California right now is funding research, which in fact I was just working on a proposal about, smart grid R&D and also education to educate the workforce that's going to be building, designing, and operating the smart grid of the future. I think there's definitely commitment of resources to it. Again, it's an interesting and solvable engineering problem, I would say. And I'm sorry I can't give you a dollar figure. But it's on the same order of magnitude, I would say, as the investment in the energy sources per se. It's not a negligible component. I'm going to take one last question. Oh, yes?
There's the concept of energy return on energy investment. For instance, with uranium, it takes all the energy to mine it and refine it, and to make the cement, the concrete for the. So you put a lot of energy in before you get anything out. Even with a photovoltaic panel, I've heard that it takes a couple of years sitting there in the sunshine generating electricity to give you as much energy out as what went in to manufacturing it and installing it and so on. I wonder if you could give us some idea of the orders of magnitude of those numbers.
Yeah, actually, for the PV, the cells have become thinner, meaning they use less silicon material, and the embodied energy goes into heating up and melting the silicon so it can be purified. But the thin film cells are actually paying for themselves in a few months, it looks like, of sitting in the sun. So it's not it's not a trivial problem, but it's been greatly ameliorated. The embodied energy for nuclear power plants, there's estimates all over the map. And really, I think, though, that it's the correct currency in which to be thinking. I mean, I would probably agree with nuclear advocates, although, I mean, you can tell I'm not a nuclear advocate. I mean, I think it's basically expensive and committing in all the wrong ways. But I would have to agree with people who say it is...
Popular sushi.
Well, personally, I wouldn't put my money in it. I wouldn't put any money in it, actually. But I think it's fair to say that the energy utilization in uranium is a pretty good deal. I mean, it's seductive because it has a very high energy density, so you get a lot of power out of a very small volume of material. Yes, you have embodied energy in the mining and enrichment and manufacturing of fuel. I think under the assumption that you have a well-tuned, functioning fuel cycle, you can make the case that the embodied energy is not too big, it's not negligible, but it's workable. The problem is, it's a really big assumption to make, to say that the whole fuel cycle is going to be operating flawlessly. And you have to make that assumption in order to not have waste. And so there we're back again to the problem of complexity, that you're committing yourself to something where very easily you will have inefficiencies. You will have expended billions of kilowatt hours building a facility that ends up not getting used because it doesn't work for some reason or other. And so the vulnerability is much greater. So I think the track record, in fact, is in line with what the critics have argued, which is that it's been more embodied energy. For carbon capture, I haven't looked at the numbers at all. But I would say that's a very legitimate point of analysis, which ultimately, if I sort of come back to the first slide, our economic analysis ought to be really in units of energy transferred, because that makes the most fundamental sense, and that would also allow us to keep in mind the finiteness and the physical constraints that we're operating under. So it is time for me to stop, but thank you so much.